Good afternoon, class. We are looking at Chapter 4, Exponential and Logarithmic Functions. Here's 4.7 Exponential and Logarithmic Models. So we're going to cover exponential and logarithmic models. The objectives are determine the future value of a lump sum of money, calculate effective rates of return, determine the present value of a lump sum of money, determine the rate of interest or time required to double a lump sum of money. So a quick recap, exponential functions are in the form of f of x equals a to the power of x, where a is larger than 0 and a can't be 1. When a is 1, you don't have an exponential function. Part B is a horizontal line. So exponential growth, exponential decay. And so in the case, in both cases, horizontal asymptote is the x-axis, y equal to 0. Vertical asymptote, you don't have any, y-intercept at 0, 1. X-intercept none, domain, all real numbers, range from 0 to infinity. When a is larger than 1, we are dealing with an exponential growth, so it's increasing. Limit of f of x as x approaches infinity is infinity. That means the first quadrant, the end behavior. Limit of f of x as x approaches minus infinity is 0. That means it establishes the fact that the x-axis or y equals 0 is the horizontal asymptote. In this case, when a is between 0 and 1, it's a decreasing function, and limit of f of x as x approaches positive infinity is 0, which establishes the horizontal asymptote, and limit of f of x as x approaches negative infinity is infinity. Now, if we look at log x base b equals y, and this arrow, okay, this is the definition we have used. Remember, the same situation with the exponential applies for logs. Base must be positive and can't be 1. And if you follow that arrow, you get b to the power y equals 6. So if we can go from one format to the next, we have no problem understanding the properties. For example, in the case of a general log, where we have the base as a or b, just anything that you establish, y equals log x base b, that means b to the power of y equals x. It gives us those properties. I have put them in a numerical order so we can go back and forth. Log 1 base b is 0, log b base b is 1, log b to the power of x base b equals x. All of those three properties just follow the arrow. Product rule, quotient rule, power rule. These two actually refer to the fact that exponential functions and logarithmic functions are inverse functions. When the base is 10, log x base 10, we don't write it, we write y equals log x. That is referred to as common log, therefore 10 to the power of y equals x, and it gives rise to the following properties. Notice, for example, log 1, you just don't need to write the base. This one, because you don't write the base, it means base 10, then in this case, the base and the argument must be the same, so log 10 equals to 1. The rest of it follows. In the case of a natural log, instead of writing log x base e, we write ln x. So it gives rise to e to the power of y equals x. And again, for this one, we just write ln 1. For this one, these two must be the same. When we write ln, the base is e, so we use e. The rest of them follow. Exponential functions and logarithmic functions are inverse functions. For example, y equals e to the power of x and y equals ln x. Therefore, they are symmetric with respect to the line y equals x. Change of base formula, log x base b is log x over log b, and you choose a base, any base you want, for example, a. However, we either choose base 10, that means common log, or base e, that means natural log, because now we can evaluate this using a calculator. What does that mean? I want to start with the middle one. Ln x equals 0 when x equals 1 refers to this point, everybody. The x-intercept on the graph of y equals ln x. Ln x is less than 0 for x being between 0 and 1. That means it's negative here. Ln x larger than 0 when x is larger than 1. They're referring to this point. So I hope it's straightforward, everybody. Exponential and logarithmic equations. Properties for solving them. If a to the power of x equals a to the power of y, because they have the same base, they must have the same exponent. X must be equal to 1. If a to the power of x and b to the power of x the same, because we have the same exponents, we must have the same base. A must be equal to 1. A must be equal to b. Same thing happens with log. If x equals y, log x base a and log y base a are the same. Of course, x and y must be positive because the arguments are always positive. Log x base a, log x base b are the same. And then the base a and b must be the same. Again, x, a, and b are all positive. Now, exponential and logarithmic models, we start with simple interest. Everybody remembers I equals PRT, where P is the principal, R is the rate, T is the time, normally in years, and I is the amount of interest. If you add this to P, you end up with the amount. If it's compounded, then the amount in one shot, we can find it as P times 1 plus R over N to the power of NT, where P is the same P, principal, R is the same R, rate, T is the same time in years, and the N is the number of compounding that takes place per year. When interest is compounded continuously, the balance A in the account at any time t can be calculated by the exponential growth. A equals PE to the power of RT. In some text, they might write P equals P sub 0 e to the power of KT. Please understand they're the same. It's just that depends on which text. In this case, the principal amount is P. In this case, the initial amount or the principal amount is P sub 0. Where P is the initial starting value of the quantity, we're talking about this one, and K is the constant growth rate. Sometimes we use R, sometimes we use K. When K or R is positive, P increases as T increases. When it's negative, P decreases and gets closer to 0 as T increases. By that, we are referring to this P, okay? Future value of a lump sum money. P equals P0 e to the power of KT if we use this formula, or A equals PE to the power of RT. That is referring to the future value. So if you look at this graph, we start with P sub 0. Normally on the left side, we don't have anything because of the negative side of the horizontal axis refers to negative time. So this is P sub 0, the initial value. Doubling time refers to the amount of times it takes that p sub 0 becomes 2 p sub 0. We get to this point, where the general formula is what you see here. Doubling time, time for the population or investment to double in size. So we go with this formula and we replace the p with 2 p sub 0. We drop p sub 0 from both sides. If we take the natural log of both sides, now remember when we discussed the previous section, because the right side has the base e, we are not going to go with a common log. We're going to take natural log. So this becomes ln2 and this becomes kt. Ln of e to the power of kt is kt. So if you want to calculate t is ln2 over k. In some instances, we may be interested in calculating k, because if that one is missing, and that's ln2 over t, the doubling time. Compound interest proof. We said compound interest is a equals p times 1 plus r over n to the power of nt, compounded n times per year. That's what we said. So let's quickly look at how it works. We know the simple interest I equals PRT. Each compounding period t equals 1 over n years. T equals 1 over n years. For example, if it gets compounded just once, t is just equal to 1. But if it gets compounded quarterly is 1/4 and so forth. So t equals 1 over n. And in this equation, we are going to replace the t with 1 over n. So p times r times 1 over n is p times r over n. So after one compounding, a is p plus I, p plus, and this is I, p r over n. And now we can take the p out, p times 1 plus r over n. After two compounding periods, a equals the new principal plus interest on new principal. So what is the new principal? This is the new principal, and the interest on that, that means this amount times r over n. So again, this is the new principal. Now the new principal times r over n gives us the amount of interest. In essence, we are using this formula. Now this is after the second one. As you can see, between the two, 1 plus r over n is in common. So we can take p times 1 plus r over n times 1 plus r over n. This is a simple factoring. 1 comes from this one, r over n comes from this second piece. Okay, everybody? Again, this entire thing is in common, which is p times the same thing to the power of 2, because these two are identical. Now, we do the same thing for the third time, just as an example. After 3 compounding period, a is new principal plus interest on the new principal, which means write this one, and then this one times r over n. And again, if you factor, this entire thing in blue is in common. This gives you 1, this gives you r over n. And the product of these two is 1 over r plus 1 plus r over n cubed. Of course, if we continue after n compounding periods, okay, so the first one we have exponent 1, we don't write it. The second one, we have exponent 2. The third one, we have exponent 3. The nth one, we must have the exponent n. So after t years, there are n times t compounding periods. That's why n t. This is after t years. All right. Find the amount A that results from investing a principal P of $2,000 at an annual rate of 8% for a time T of 1 year. So what is given? The principal is $2,000. The rate is 0.08 or 8%. T is 1. And we are going to use compounded monthly. That means n equals 12 with the formula we established in the previous page. You all remember this from algebra. So A equals P, replace it with 2000. 1 plus R is 0.08, divided by N is 12 to the power of N, which is 12 times T, which is 1 year. And you just add these two, raise it to the power of 12, multiplied by 2000. You put it into a calculator, you get this one. And we are going to normally, with dealing with money, we are going to round it to 2 decimals. And when we go with to 9, we have to change here. We have to change here. So it becomes $2,165.00. You have to deal with 2 decimals when it comes to money. Okay, unless they tell you otherwise. Now, compounded continuously uses this formula. So A is equal to the amount of principal is 2000, e to the power of R, which is 0.08 times T, which is 1. That's why when you write the given, it really makes it easy to follow, everybody. You just plug it into a calculator and it gives you this number. Again, we are going to go with 2 decimals. So after 7 is 4, we keep it as 57 and we read $2,166.57. Obviously, as we add to the to n, this gets larger and ultimately becomes continuously, and it's even larger. Not by much, but it depends on a lot of factors. The amount of principal, the number of years, then you'll see some difference. Now, the continuous compounding is what we established here. Let's look at the justification for that. If we let n over r be something like m, some variable, not n, not r, not p, not a, for example, m. So that means this is 1 over n, and that means the cross product n is mr, and over here we can replace the n with that. And rewrite it in this manner. So P times 1 plus 1 over M to the power of M R T, and So we are replacing the m with mr. We keep the m in, we take the r out, it doesn't matter. Remember, the power rule says you have to multiply all these three. This expression, E, is this expression as m goes to infinity, the limit of 1 plus 1 over m as m to the power of m as m goes to infinity, and it becomes a equals p e to the power of rt. So this expression, if you plug in numbers 1, 2, 3, 4, 5, as you get make it larger and larger, and the same thing here, it ultimately goes to E. This is one way to define E. There are other ways as well. We'll discuss it in calculus. Calculate effective rates of return. Suppose that you have $1,000 and a bank offers to pay you 3% annual interest on a saving account with interest compounded monthly in 1 year. So you're going to say A equals P times 1 plus R over N to the power of NT. We have $1,000, that's the P. R is 0.03. A T is 1 year. And monthly means N must be 12. Plug in. You divide this one by this one, you add it to 1, you raise it to the power of 12 times 1,000, and it gives you this number. $1,030.42. Remember, we do the rounding to 2 decimals. So how much did we make from 1,000 to $1,030.42? This amount is the amount of interest. So the interest earned is $30.42. Using I equals PRT with T equals 1, I equals 30.42, and P equals 1,000, we find the annual simple interest rate is 0.03042 or 3.042%. This interest rate is known as the effective rate of interest. In other words, whatever that they give you, however they compound it, the effective rate says, what if it doesn't get compounded? What if it's a simple interest? What is then? What is the equivalent rate? Okay, that's the definition. So the effective rate of interest is the equivalent annual simple interest of interest that would yield the same amount as compounding after 1 year. So this is because of the compounding, the 3% compounding results in this. That means because of the compounding 12 times, we got a little bit more than 3% for the simple interest, we got 3.042%. This is the equivalent rate or effective rate. So with that being the case, let's calculate effective rate of return in this manner. We said I equals PRT, A equals P plus I, P times 1 plus RT. This is a simple interest. This is the amount we end up after using that, and of course, whatever T might be. However, effective rate refers to T being 1 year. So in this formula, we must set T to be 1. And now, when T is 1, instead of R, we're going to call it R sub E, the effective rate. Let's look at the compound interest and see what we get. We have this formula for the compounding. Let's use T equals 1 for this one. We want to see the equivalently what happens. And this is what we get. Now, this amount, we set it equal to this amount. Set this to equal. So when you set them equal, I want you to look at this part and this part. Never mind, they're all A. So I can get rid of P this is the left side, this is the right side, they must be equal. Let me erase this and let me just put this. So this is equal to this. So what is R effective? The right side minus 1. So R effective is 1 plus R over n to the power of n minus 1 for compound interest. What about compounded continuously? Well, we know the formula is A equals P e to the power of RT. So we're going to say, and T is equal to 1. T is equal to 1. And we're going to set that equal to this. And again, we're going to get rid of the P. So 1 plus RE is equal to e to the power of R. So RE is the right side minus 1. And in the case of compounded continuously, RE is e to the power of R minus 1. Let's look at an example to put all of this together. Calculate effective rates of return, which is the best deal. Suppose you want to open a money market account. You visit 3 banks to determine their money market rates. Bank A offers you 4% annual interest compounded daily. Bank B offers you 4.1% compounded monthly. And Bank C offers 3.95% compounded continuously. Determine which bank is offering the best deal. So first and foremost, we got to put the rates. So Bank A gives us 4%. Bank B, 4.1%. Bank C, 3.95%. First, establishing that. This is compounded daily, this is compounded monthly, and the R effective is 1 plus R over n to the power of n minus 1. This one does it continuously. R effective is e to the power of R minus 1. This one does it daily, so n is 365, n is 12 here. So we just want to make sure that we establish what's going on. Okay, everybody? So basically, we are going to plug in. Let's calculate R effective for this one. 1 plus 0.04 divided by 365 to the power of 365 minus 1. So just following this formula. Using a calculator, we end up with this, which is about 4.08. And if we stop here, this changes to 1. Plus this 8 makes this one to go to 4.081%. For this one, we're going to put it into the same formula. We're going to replace the R with 4.1%, that means 0.041, and N with 12. Using a calculator, we get 0.041793. So that means you go 2 decimals to the right, 4.17, and because next to it is 7 changes to 8. So 4.178%. In this case, into this formula, we put e to the power of R, that means 0.0395, and subtract 1. Gives you this number, You move the decimal to the right by 2, you get 4%, 4.02905. So if you stop here, next to the 0, so it doesn't change. And all you have to do, compare these three numbers. Clearly, this is the largest among the three. That means Bank B that offers 4.1% compounded monthly is offering the best. Not just because 4.1% is larger than those two, the effective rate ends up being larger. So you have to establish that. If there was a bigger difference among those, you could have seen that. Determine the present value of a lump sum of money. We know A is P times 1 plus R over N to the power of NT for compound interest. We know A is equal to P e to the power of RT. Okay. And so for this one, you want to solve for P. That means you divide by this. Division by this means multiplying by the same thing to the power of negative. For this one, you divide by this. Division by this expression, that means multiplying it by the same thing to the power of negative. So one more time, this one, to divide by this to find P, if you multiply this one by the same thing but a negative exponent, that means division, everybody. Because remember, this goes down, right? This goes down and takes a positive value, positive exponent, same thing. So a zero coupon, non-interest bearing bond can be redeemed in 10 years for $1,000. How much should you be willing to pay for it now if you want a return of 7% compounded monthly, B 6% compounded continuously? This one uses this formula. Please understand what's going on here, okay? R is 0.07, N is 12, okay? A, $1,000, 10 years, okay? That's the given from here. That's the amount we want. And in this case, R is 0.07, N is 12. If you put that into this, you have to find P, okay? Or just put it into this one, makes no difference. But this in one shot gives you the answer. So put it into this, that means P is A, which is 1,000, 1 plus R, which is 0.07, divided by N, which is 12, and raise it to the power of negative N, which is 12, times the T, which is 10. You put that into a calculator, you go with two decimals, you get $497.60. That means if you put this much and they give us 7% compounded monthly over 10 years, we get $1,000. What about this case? Put it into this formula. A is 1,000, e to the power of negative R. R is 6%, 0.06, everybody. 6%, 0.06. And T is 10. And again, you use a calculator, we end up with 548.81. That means if we put $548.81 today, in 10 years, we get $1,000. That's the meaning of it, everybody. I hope everybody's clear on that. We are going to move on. So that's a present value, everybody. Determine the time required to double or triple a lump sum of money. And we have established that. How long will it take for an investment to double in value if it earns 6% compounded continuously? Now, we have established that, and we can use that. So simply put, the fastest way would be to divide ln2 by k, which is 0.06. But just to establish it one more time, 2 times the p is p times e to the power 0.06. We are looking at this one or this one, doesn't matter. Okay. So a is 2 times p because you're doubling, and then p e to the power 0.060. What we did here, we did it in general. We kept it at k or r. Obviously, the p cancel out from both sides, meaning these two drop. And if you take the natural log of both sides, the right side becomes simply 0.06 t. And if you divide by 0.06, see if we had used this formula, and you could use it, but we want to know why we are using it. It gives you 11.55 years. So it takes, if it's a 6%, it takes more than 11 years to double up in value. How long will it take to triple? That's why I did that, because we don't have a formula for the triple. I want to go over that and show you how we arrive at it. Okay. And so this formula, the left side is 3p because we want it triple. Okay. 3 times as much. So we go this formula and we do that, and we are going to cross the p, right? And then we're going to take the natural log of both sides, and the right side becomes 0.06t, and you divide by 0.06. So the precise answer is ln3 divided by 0.06, and you use a calculator, takes 18.31 years. So in essence, for triple ln, for double ln2 over k, for this one would be ln3 divided by k. We established it in that manner. If an account pays 8% annual interest, compounded continuously, how long will it take a deposit of $25,000 to produce an account balance of $100,000? We can plug into the formula to see what we get, because R given as 0.08, P is 25K, A is 100,000, and T is missing. You can plug it in. I want to show you, if you want to solve it in general class, for example, A equals P e to the power of RT if I divide by P. I want to show you something in general. I can take the natural log of both sides, and the right side becomes RT. And if I'm interested in T, would be the left side divided by R. So T is ln of A over P divided by R, or this you can say ln A minus ln P, but doesn't matter. In fact, one may be interested in calculating R, and that's ln of A over P divided by T. That would be also a possibility of solving for rate, if the rate is missing. So in any event, we mentioned that R is 0.08, P is 25K, A is 100K, and now if we want to go with the formula, we are going to go with ln of A over P. That means natural log of 100,000 divided by 25,000 divided by 0.08. And you can say 100K over 25K. As you know, this is 4. So ln4 divided by 0.08, put it into a calculator, results in approximately 17.33 years. It is an approximation. You really um, have to decide how many decimals. Normally they tell you. What annual rate of interest compounded quarterly should you seek if you want to double your investment in 6 years? And so that's the formula where what is given compounded quarterly, n is 4. To double your investment, A becomes 2 times P, and the T is 6 years. So that's the first thing I want you to see, everybody. Now, into this formula, we are going to replace the A with 2P, R is missing, and we replace it with 4, over here 4, and T we will replace it with 6. So that's why you write the given, it makes it easier that. And so 4 times 6 is 24. Now, remember, we want to solve for R, so this is being raised to the power of 24. We have to take the root. So if we take the 24th root, then the right side simply becomes 1 over R to the power of 4. And I'm going to move the 1, becomes this minus 1. And then I'm going to multiply it by 4. And we get R equals 4 times 24th root of 2 minus 1. So you use a calculator to find this, subtract 1 times 4, and it gives you this number, which is about 11.72. Next to it is 0, so nothing happens. The annual rate of interest needed to double the principal in 6 years is almost 12%, 11.72%. Find the equation of populations that obey the law of uninhibited growth, meaning A of t is A0 e to the power of kt when k is larger than 0, exponential growth, and A of t equals A sub 0 e to the power of kt, k is less than 0. This is exponential decay. So, definition recall. If P sub 0 is invested once, P sub 0 can be investment or can be population. For t years at interest rate of k, or again, as I said, in some cases we use r, compounded continuously, then P of t equals P sub 0 e to the power of kt, where P equals P sub 0 at t equals 0. P of t is the future value, P of 0 is the present value. Interest rate is either k or r, so sometimes we use k, sometimes we use r, depending on the text. T is the number of years. And again, various ways of writing the same thing, class. A of t is A sub 0 e to the power of kt, P of t is P sub 0 e to the power of kt, P sub 0 e to the power of rt. So k or r, k is the same as r, depending on the text, class. So we may use k or r, okay. We may use P sub 0 or A sub 0. Okay, that means the initial value, the present value. Okay. And if we use A of t, that is the future value. If you use P of t, that is the future. And the doubling time is ln2 divided by t. We established that when we went over that. See, ln2 divided by k, okay, and k was ln2 divided by t. I have shown you that. You can go back to the note and see that. And this doubling time, okay, gives you ln2 divided by t. Now, if we go with the half-life, then we can go with ln of 1/2 over t. Half-life, time for substance to decay to half of its original size. Okay, that's what half-life is all about, and you can establish that as well. A colony of bacteria grows according to the law of uninhibited growth according to the function n of t equals 90 e to the power 0.05 t, where n is the number of cells and t is measured in days. So let's see what that means. Initial value, this number, n of 0 or n sub 0 is 90 e to the power 0.05. Replace that with 0 and you get 90. You may recognize just this as the initial value, but here's the proof. Replace the t with 0. Okay. Now the growth rate, they are referring to k, which is 0.05 or 5%. Population after 5 days. Well, into this formula, we are going to replace the t with whatever they gave us, which is 5. And you put that into a calculator and you round it to the nearest whole number, 116 cells. When will it reach 140? That this number, this 90 e to the power 0.05 t formula equals to 140 and solve for t. That's all. So divide by 90, you get 14 over 9. Take a natural log of both sides. And this becomes ln of 14 over 9. And the right side becomes simply the exponent 0.05 t by logarithmic properties. We want the t. So t is the left side, ln of 14 over 9 divided by 0.05. Both sides divide by 0.05. And now this goes into a calculator and gives us 8.8 days. Again, maybe a number of decimals, and then do the rounding. Doubling time, again, you can use class ln2 divided by k, which is ln2 divided by 0.05. Just to show you again one more time, you replace this one with 180 because this is the initial value. And then divide by 90, you get 2. Okay, right? And then you say natural log of the left is natural log of the right. And you get ln2 equals 0.05 t, or ln2. We just established that it becomes what we have known all along. Okay, so my point is, again, you'll be exposed to that, but it is up to you whether you want to use the formula that we established, or you establish it from the get-go. It's your choice. It's up to you. I have no problem with that. Either way is fine with me. And so, of course, using a calculator and some um, decimals, 13.9, almost 14 days. A colony of bacteria increases according to the law of uninhibited growth if n is the number of cells and doubles in 5 hours. And t is the time in hours, express n as a function of t. Now, the bottom line is we want to go with this formula, everybody. And all they are really asking us, because they have given us the doubling time, you have to establish the value of k. And you can use ln2 divided by t, which is 5, ln2 divided by 5. You can use that, and that's absolutely fine. If you want to establish it again using this formula, this is the same formula that was mentioned. Okay. Okay, everybody. So in essence, we are using the doubling 2 times n sub 0 to prove the formula again. And you don't have to do that. We've done it a number of times. And you get 2, and you take the natural log, and that becomes ln2, and this becomes 5k. And again, we get to the same formula that we had. So that's just as good. Now, this time I put a lot of decimals because we want to go with the exact, really. So either use ln2 over 5 precisely, or just use a lot of decimals. When you want to find out the answer to part B, if there are 10,000 cells initially, how long will it take for them to be 25,000? That is really important to have a lot of decimals here. So simply put, into this formula, the left side is given as 25,000. N sub 0 is given as 10,000. And e to the power of kt, I'm going to stick with ln2 over 5 because I want to go with exact. Okay, so go with that. Okay. That's the same formula, but much more precise is what you see here. And now we have this. Divide by 10k, both sides. And you get 5 halves on the left. And let me erase and show you the next step, taking the natural log of both sides. So ln of the left is ln of 5 halves. Ln of the right is just the exponent, which is ln2 over 5 times t. If you divide ln 5 halves over ln 2/5, okay, ln2 over 5, and use a calculator, you get 6.61 hours. Why hours? Because over here, the units are given as hours. Okay. So I hope it's clear to everybody. Pretty straightforward. A colony of bacteria grows according to the law of uninhibited growth, where n is the number of cells and t is measured in hours. Express n as a function of t. Okay, so that's the general form. If the number of bacteria doubles in 2 hours, find the function that gives the number of cells in the culture. And you can establish just the way we did it before. You don't have to class, okay? You can just use the formula that was mentioned in the previous page. As you recall, T was ln2 from the previous page. I'm reminding you that. T was ln2 divided by K, and K was ln2 divided by T, and therefore you can say ln2 divided by T, which is 2. You don't have to go through the process, okay? Because we have established this before. But in this case, you drop n sub 0. You take the natural log of both sides. And the right side becomes 2k, and you divide by 2. And that's k. I want you to see this one using this formula, ln2 divided by t. And of course, you can write n of t, n sub 0, e to the power of that number, or just precisely ln2 over 2. How long will it take to triple in size? Now you are going to use 3 here instead of 2. They cancel each other. Take a natural log. The left side is ln3, the right side is this number, or ln2 divided by 2. Class, precisely, instead of that, the t remains. Instead of that, you can say ln2 divided by 2. In any event, t is the left side divided by either that number or ln2 divided by 2, and we get ln3 divided by that number, about 3.2 hours. Now this is easy. Doubling time for second time, that means getting it to 4 times. If it doubles in 2 hours, it doubles again in 2 hours, so that means 4 times, so in 4 hours. So again, if it doubles in 2 hours, then in 2 hours it doubles again, becomes, in 4 hours, it becomes 4 times. It doubles again in 8 hours, okay? That means 8 times. Find the equation of a population that obey the law of decay. A bone is found to have 45% of the original amount of carbon-14 if the half-life of carbon-14 is 5,600 years. How old is the bone? Well, let's remind everybody of carbon-14 dating. Also known as radiocarbon dating is a method used to determine the age of organic materials based on the decay rate of carbon-14 isotope. Carbon-14 is a radioactive isotope of carbon that is naturally present in atmosphere and is constantly being produced through cosmic ray interactions. Living organisms absorb carbon-14, we breathe in essence, through processes such as photosynthesis or consumption of other organisms. When an organism dies, it stops taking in new carbon-14. and the carbon-14 present in its tissues begin to decay at a known rate. By measuring the amount of carbon-14 remaining in a sample and comparing it to the initial amount present when the organism was alive, scientists can estimate the time elapsed since the organism's death. This method is particularly useful for dating organic materials up to about 50,000 years old, making it valuable for archaeological and geological research. There are other methods that are being used nowadays, but just this is one of them, a scientific methodology. So we have a of t equals a sub 0 e to the power of kt. If k is less than 0, it's a decay, or sometimes they use minus kt. It depends whether you use the negative or not, and t becomes ln of 1/2 over k. Let me go through the process for you. The formula is this, class, so we want to discuss the half-life. The formula is this, and if you go with that, half-life, that means the initial amount, whatever it is, we end up with half of that. So 1/2 of a sub 0. This is the concept of a half-life, everybody. Half-life. So we drop the a sub 0 from both sides. We take a natural log of each side. The left side is ln of 1/2 or ln of 1 minus ln of 2. And the right side is the exponent. KT. You can even keep it as KT if you want, class. Or 5600K in this case. So what is K? ln of 1/2 divided by 5600. In other words, class, if you just keep this as a T, then it establishes T equals ln of 1/2 over K. So I want to make sure we understand what's happening here. When we don't write negative, this is what we get. If we write negative, we just have ln of 2 over K. In any event, so that's the K. You put that into a calculator. ln of 1/2 is a negative number, so negative 0.000124. If you go with the formula that we had before, T equals ln 2 over K, that means we use then this formula, okay, if you use the, and we put the negative intact here. In any event, now let's plug this one in. A of t becomes a sub 0 e to the power of this number times t. So that is establishing the formula according to the information for the half-life. By the way, in some places they take it 5,700 years, in some places, because that's an approximation, somewhere in between, okay, just in case if you come across that. So we established the formula. How much is left? 45%. So replace this with 0.45 a sub 0. Drop this. Take a natural log of both sides, and the right side just becomes its exponent. And the t is the left side divided by this number, negative 0.000124. Put it into a calculator, and bear in mind, ln of 0.45 is negative, over negative makes it positive. So 6,451 years. Again, this is an approximation. Normally they go with the whole number. You don't have to, but understand that it's an approximation. Here's the last question, everybody. An ancient burned tree contains 1.67% of the original amount of carbon-40. The half-life is 5600. How old is the tree? Well, we have the formula, and we remember we have this. So I'm going to use the formula we established in the previous page. You don't have to even write this stuff. This is the formula that we found in the previous page. However, if we didn't have that, we have to go through the process, okay? You may remember Elena 1/2 over 5600. And again, in some, they may change this number, okay? Because it's somewhere between 5600 and 5700. So Elena 1/2 over K is T. And K is Elena 1/2 over T. All right. So with that being the case, now 1.67% left. 1.67%, you move the decimal to the left by 2, becomes 0.0167 A sub 0. I hope you understand this number is this one, okay? This much of the original. So you can drop the A sub 0, everybody. And now you take the natural log. The reason we take the natural log, because the base is E here. So the left side is the left side, the right side becomes its exponent only. So you divide both sides by this number. That's your answer. You put it into a calculator. 33,003 years, that's a lot. So it's 1.657% left. It takes that long for most of it to decay. We have only 1.67% left.